Hey guys, welcome back to the Blimp video channel. My name is Craig Enders and I appreciate you tuning in. In this video, I'm going to describe how Blimp treats incomplete predictor variables. I'll illustrate two different model specifications and I'll show you how these setups accommodate variables with different metrics. Before we get started, I want to acknowledge the Institute of Educational Sciences for their support and point you to the project's website. You can download Blimp at the same homepage. Click the subscribe button in YouTube to get alerts when I post new videos to the page. Okay, so in some previous videos, I explained that Blimp uses a factored regression specification that divides a multivariate distribution into a sequence of simpler distributions. And beyond acknowledging that that multivariate distribution exists, this factorization procedure doesn't make any assumptions about the shape or form of the distribution. Rather, assumptions enter on a variable by variable or model by model basis. As a rule, any variable with missing data requires a distributional assumption. In Blimp, there are two ways to assign distributions to incomplete predictors. The first approach assigns a multivariate distribution to the regressors. The outcome has a distinct distribution that can be different. In the path diagram, I have the two predictors and outcome in different colored sandboxes to convey that Blimp is invoking two statistical models, each with unique distributions. Focusing on the predictors, the residual arrows convey that the variables have a distribution, and the curved arrow represents their correlation. This specification is very simple to implement, and it allows normal, binary, ordinal, and multi-categorical predictors. A sequential specification provides a second way to model incomplete predictors. The sequential specification represents the multivariate distribution as a set of univariate regression models, each with its own distribution. Essentially, each predictor becomes a dependent variable in its own regression equation, and we use a path diagram to represent the associations among the predictors. In the diagram on this slide, I again show the variables in different colored sandboxes to convey that Blimp is invoking three statistical models, each with its own distribution. X1's model is empty as there are no incoming arrows beyond its residual. In lieu of a correlation, X1 and X2 are connected via a regression slope in X2's model. The advantage of the sequential specification is that it allows for a broader range of outcome variable types, and predictors can also be nonlinearly related. For example, X1 could have a nonlinear influence on X2. So let's dig a little bit deeper into these two specifications. To make the illustration more concrete, I'll use data from an educational study. The data in the analysis scripts are on the project's webpage. The file includes assessments of broad reading in first grade and ninth grade. The data also contain teacher ratings of behavioral symptoms and learning problems from the first grade, as well as a categorical classification indicating risk for emotional or behavioral disorders. Let's start with a linear regression model that uses the three continuous measures from first grade as predictors of ninth grade reading performance. In the path diagram, I again have the predictors and outcome in different colored sandboxes to convey that Blimp is invoking two distinct statistical models, each with its own assumptions. The left side of the screen shows the model command for the analysis. A single line of code is all that's needed to specify the entire model. The tilde is like an equal sign in a regression equation, with the outcome variable to the left and the predictors to the right. So all we need to do is specify the dependent variables regression, and Blimp automatically figures how to set up the predictor models. Any outcome variable that appears to the left of a tilde has its own table with parameter estimates and effect sizes. The results are listed in a section labeled Outcome Model Estimates. In the interest of full disclosure, Blimp also prints estimates for the predictor models. These estimates are not of substantive interest, and you wouldn't report them in a paper. These additional tables show up under the heading labeled Predictor Model Estimates. Each incomplete predictor has its own table displaying regression coefficients linking it to the other predictors. The table here displays the estimates from the behavioral symptoms model. The previous code assumes that all predictors have missing values, which they do in this example. Complete predictors, if you have them, don't require a model because there are no missing values to impute. So in most cases, it's a good idea to simplify estimation by telling Blimp not to estimate a model for these variables. Let's pretend that the learning problem's rating variable is complete and does not require a distribution for imputation. Looking at the code on the left, listing the complete predictor after the fixed command takes care of that. In the path diagram on the right, you'll notice that the learning problems variable doesn't have a residual arrow pointing into it. That indicates that the variable doesn't require a distribution. However, the predictor still conveys its information via straight arrows connecting it to the other predictors. Next, let's replace one of the continuous predictors with a binary predictor. The dataset has a dichotomous variable measuring student risk for developing emotional or behavioral disorders. The variable is a dummy code with 0 denoting low risk and 1 indicating medium or high risk. In other videos, I explained that Blimp uses a latent response variable framework to accommodate categorical variables. For example, a binary variable imagines a normally distributed latent variable with a threshold cut point that divides the continuous propensity distribution into 2 segments. An ordinal variable is similar but requires multiple threshold parameters to divide the distribution into discrete segments. Finally, multi-categorical variables use multiple latent variables that are analogous to continuous versions of dummy variables. The diagram shows a 3-category nominal variable that requires a pair of latent response scores for each individual. In this data set, approximately 66% of the students are classified as medium or high risk and 34% are low risk. The graph on the right shows the latent risk status distribution. A threshold parameter divides the continuous propensity into 2 segments such that the areas under the curve match the bar plot proportions. Because the latent variable is unobserved, its residual variance is fixed to 1 to establish a scale, and the threshold cut point is fixed at 0 to establish the mean structure. The latent variable mean is an estimated parameter. In this example, the mean is positive because the threshold has to be below the mean in order to get 66% in the upper tail. Discrete variables like risk status exist in 2 different states. Predictors are governed by a multivariate normal distribution that uses the latent response variable, and the discrete dummy code simultaneously appears as a regressor in the focal regression model. Designating a variable on the ordinal line invokes a categorical variable regression model for the binary predictor. The path diagram uses an oval to represent the continuous latent variable. Notice that the continuous predictors correlate with the latent response variable, which is why Blimp can assign a multivariate normal distribution to the predictors. The broken arrow represents a nonlinear link function that maps the latent variable to the binary dummy code, which appears as a rectangle in the diagram. Finally, it's this dummy code that predicts the dependent variable. Importantly, all of this happens under the hood and behind the scenes. A single line of code is all that's needed to specify the entire model. You could also use the nominal command to identify the binary variable. The underlying statistical model is identical. I also want to highlight that continuous and discrete variables can be centered at their iteratively estimated grand means. Here I use the center command to deviate all 3 predictors at their means. Although it may seem unnatural to center dummy codes, it's perfectly fine. All you're really doing is converting the dummy code to a contrast code such that the regression intercept becomes the grand mean. Next, let's take a look at a multi-categorical predictor with 3 levels. The dataset also has a 3-category nominal variable that classifies students into low, medium, and high risk groups. The numeric codes are 1, 2, and 3. The regression model for multi-categorical predictors does not use threshold parameters. Rather, the multinomial probit model defines a latent propensity variable for each category. Then it creates a latent difference score that compares the latent values for 2 of the 3 categories to that of the reference group. Conceptually, the pair of latent variables shown on the right are like continuous versions of dummy variables, as they represent a continuous propensity for classification in one group relative to the reference category. Like the binary variable, multi-categorical predictors exist in 2 different states. The regressors are again governed by a multivariate normal distribution that uses the latent response scores, and the dummy code simultaneously appear as predictors in the focal regression. So again, let's take a look at the path diagram. To begin, you define multi-categorical predictors on the nominal line like I show here. Importantly, you don't want to create the dummy codes ahead of time. You simply list the original variable name on the nominal and model lines, and Blimp creates the dummy codes for you on the fly. By default, Blimp uses the lowest numeric code as the reference category, in this case a 1. The path diagram on the right uses ovals to represent the pair of continuous latent variables. Notice that the continuous predictor correlates with the latent response variables, which again is why Blimp can assign a multivariate normal distribution to the regressors. The broken arrows represent a nonlinear link function that maps the latent variables to the binary dummy codes, which then appear as rectangles in the diagram. Finally, the pair of dummy codes predicts the dependent variable. Like a complete data analysis, the code variable slopes represent mean differences between group 2 and the reference group 1, and group 3 and group 1. The main summary table lists these variables as risk group.2 and risk group.3. In the previous code, I listed the original variable name on the nominal and model lines, and Blimp created the dummy codes automatically. Sometimes you may want to reference the dummy codes by name on the model line. For example, if you wanted to specify a 2-degree of freedom chi-square test to evaluate whether the pair of code variables contributes to the model. Internally, Blimp identifies dummy codes by appending a dot and a numeric value to the end of the nominal variable's name. In this example, the dummy codes represent comparisons of group 2 and group 3 to the reference group, which is coded 1. You could reference these code variables by listing riskgroup.2 and riskgroup.3 on the model line like I show here. These are the same variable names that appear on the output. As I mentioned, Blimp automatically assigns the lowest numeric code as the reference group. You can change this by listing the desired reference group code on the nominal line. In this example, I designate group 3, the high-risk group, as the reference. The dummy codes now compare groups 1 and 2 relative to reference group 3. Like before, you could reference these code variables directly by listing riskgroup.1 and riskgroup.2 on the model line. A sequential specification provides a second way to model incomplete predictors. The sequential setup represents the multivariate distribution as a set of univariate regression models, each with its own distribution. Essentially, each predictor becomes a dependent variable in its own regression equation, and we use a path model to represent the associations among the predictors. So let's take a look at a model with one binary and one continuous predictor. In this example, there are two ways to set up a sequential specification. They usually don't matter in practice, so the choice is mostly arbitrary. In the path diagram, read1 is an exogenous variable with no incoming arrows beyond its residual. To specify an empty model, you just list a 1 for the intercept after the tilde, as I do here. The second regression on the model line features read1 predicting the at-risk indicator. Because the variable to the left of the tilde is categorical, this model is a probit regression with the latent variable as the outcome. As before, the broken arrow represents a nonlinear link function that maps the latent variable to the binary dummy code, which appears as a rectangle in the diagram. One advantage of the sequential specification is that it allows nonlinear associations among the predictors. For example, you could specify a curvilinear association between the two regressors by squaring the read1 predictor directly in the regression model like I show here. You could do this for theoretical reasons or as a hedge against misspecifying their association. Finally, the last regression on the model line is the focal model, which features the dummy code predicting the dependent variable. The second way to set up the model reverses the arrows connecting the predictors. In this path diagram, the at-risk indicator is an exogenous variable with no incoming arrows. As before, the first regression after the model line specifies an empty model by listing a 1 for the intercept after the tilde. Because the variable to the left of the tilde is categorical, this model is a probit regression with a latent variable as the outcome. The second equation on the model line features the risk indicator predicting first-grade reading scores. Importantly, the binary dummy code rather than the latent response variable is the regressor in this model. The focal regression model with 9th grade reading scores at the outcome doesn't change. Finally, I want to show you how to incorporate non-normal predictors into the model. Blimp uses a transformation procedure based on the Yao-Johnson normal distribution. In this case, the latent variable is essentially a normalized version of the non-normal manifest variable, and a shape parameter that works like a link function maps the normalized scores to the skewed metric. The Yao-Johnson procedure subsumes common methods like logarithmic and Box-Cox transformations, but it's more convenient because we don't have to choose a transformation in advance. The shape parameter is iteratively estimated according to the shape of the observed data distribution. We also don't need to rescale variables to avoid 0 because the Yao-Johnson procedure allows for positive and negative scores. So let's take a look at the Blimp code for this. To illustrate, suppose that the first grade learning problems variable is positively skewed. To invoke the Yao-Johnson transformation, you simply list the variable name inside the yjt function to the left of the tilde. The path diagram on the right emphasizes that the continuous predictor read1 is influencing the normalized latent version of learning problems, which avoids misspecifying the incomplete variable's error distribution. Finally, the broken arrow represents a nonlinear function that maps the normalized scores to the non-normal variable, and the skewed manifest variable predicts the outcome. That concludes our overview of working with incomplete predictor variables in Blimp. Thanks again for tuning in, and I hope you check out future videos.